So let's move on, and I'm going to give you another activity to work on. And I want you to read through this, and I want you to really use your brain power from that equipartition theorem to see if you can come up with an equation for the kinetic energy of a noble gas as a function of temperature. And I say noble gas just because we're talking about a perfect atom. A perfect atom, it's not going to vibrate. It has no bonds to vibrate against. And when it rotates, as we'll learn later, it has no moment of inertia because it's just an atom. So we're not worried about its rotation. So the only thing we're worried about with this is really like thinking about the translations. And we can also think about the electronic transitions. But for now, just kind of think about how we calculate the energy of an object in kinetic motion. So that's your hint. Okay, so think through these things, pause it if you want, or I'm going to play a little bit of music and you can kind of follow along. Okay.
Welcome to the world of the plastic beach.
Okay, so this is kind of an obscure, asking you to kind of think through this. But if we think about a molecule, or in this case, just a noble gas, right? Translating around, it's free to move in the x direction. And for a gas, the plus x will be the same as the minus x, right? There will be no difference between those dimensions. As we shall see in liquids and solids, movement in the positive x direction and movement in the negative x direction is significant because liquids and solids are compact together. They might have a neighbor that's different in the negative direction as the positive direction. But for gases, there's only 3 of these contributions, x, y, z, because of the way that it can move around and it's not close to any other neighbors. Okay, so if we know each quadratic contribution contributes 1/2 kBt, we have 3 of them, then the kinetic energy of all atoms is 3/2 k Boltzmann T for a single atom, or 3/2 RT for a molecule, or 3/2 RT for, a mole of atoms. Okay, so 3/2 kBt is the kinetic energy. Maybe you remember that equation from Chem 109. This is where it comes from. It comes from the equipartition theorem. Okay, so if we go ahead and calculate that, right, we know the value of Boltzmann's constant is 1.38, 2 sig figs is perfectly fine, times 10 minus 23 joule per Kelvin. And I think I asked you to calculate this at room temperature. So then times 298 Kelvin, and I get 6.2. I'm going to take away another sig fig because this is really just for approximate. 6.2 times 10 minus 21 joules is the average kinetic energy of a noble gas at 298 K. So that's not particularly a useful number. So make sure that you can do this. I'm just going to write the results down. But if I wanted to convert this into electron volts, this would be 38.7 milli electron volt. Practice it. Make sure that you can arrive at that number. And this would also be 3.7 kilojoules per mole. Okay? So now the question is, I think that I asked, let me go back to that slide. How does this compare to the quantized modes? Let's see, do I have, nope, not the next slide. So how does that compare to the quantized modes? 3.7 kilojoules per mole. So let's back up for a second. And we talked about, I'm going to write that number down, okay? 3.7 kilojoules per mole. So what does that number mean? What that number means is at 298 Kelvin, a noble gas, and we'll talk about how to scale that up for molecules and such, but a noble gas has 3.7 kilojoules per mole of available thermal energy. So, does it have enough energy to self-promote to an upper electronic level? Absolutely not. It needs about 1,000 kilojoules per mole. This is why at room temperature, everything is in the ground state. Practically everything, okay? Well, what about the vibrational levels, okay? Well, you need about 10 to 100 kilojoules per mole, and that's a range, right? But even so, 3.7 kilojoules per mole is not enough energy to be into an elevated vibrational level, even though technically it's a noble gas and it doesn't have a bond to vibrate on. But if we had a similar molecule with that kinetic energy, 3.7 kilojoule per mole, it has to exist in the ground vibrational state. It does not have enough thermal energy, thermal kinetic energy, to self-promote to an upper lying vibrational level. Now, the rotational levels are only spread out by single millielectron volts, which is like 10 joules per mole. So we have more than enough thermal energy at room temperature to have a series of populated rotational levels. And that's true for atoms and that's true for molecules, okay? And then the continuum, these energy levels are crazy small together, sub-millielectron volt. So this is why, if I move forward a little bit here, this is why we see at 298 K, at this temperature, there will be a population of translational levels. There will be, some maximum population level, and it's going to have a distribution. It's actually going to be shaped like some type of curve. It's not a bell curve, it's a Boltzmann's curve, and we're going to explore that more soon. The rotational levels are also going to have some population of states. Okay, so when I say population of states, this is really what I'm referring to. However, the vibrational levels, 99.99999% of everything will be in the ground state. And with the electronic levels, 99.999999999% of everything will be in the ground state. Okay, so hopefully connecting, I'm going to end this lecture now. Big take-home message. Everything is in the ground state at room temperature for the electronic levels. Practically everything is in the ground state at room temperature for the vibrational levels, and the rotations and the translations have a population of states due to the available thermal energy. And as we shall see, because of those populations of states and the rotations and the translations, that energy can be harnessed. It can be used to do stuff. It can be used to transfer energy to other molecules upon collision. It can be used to convert into potential energy. So this is all kinetic that we're talking about, okay? So these are really reservoirs of thermal energy. Thermal energy can't just exist. It has to go into these molecular modes of motion. And at room temperature, the translations and the rotations represent a reservoir for this available thermal energy.